Okay, guys, I think let's get started. So today, Shaun Miller is going to talk about the quantum gates from the security point of view, which is part of the project that we're working on, left reduction software.
Thank you. All right, thanks for that introduction. And yeah, so we're going to be discussing a little bit about just the introduction to quantum computation. So we'll talk a little bit about qubits, quantum gates, and eventually I'll discuss how this, maybe how quantum computation affects the NIST security requirements. So if you were on my preliminary exam, this last section is going to seem very familiar. However, hopefully it'll still be something useful out of the talk. I switched it up a little bit because I initially wanted to eventually implement a while loop using quantum computation, but that ended up being a little more involved for this talk, so I think it will be nice to actually talk about some of the NIST security requirements, especially because there's a lot of people from our coffee group here as well. So I just want to start with a kind of ugly table. There's really only one column, there are two columns I want you to focus on. That's the name of the scheme and the claimed security level. You'll notice that there's a section for quantum. So as you probably all know, RSA and elliptic curve Diffie-Hellman can be broken by a quantum computer. That's why, well, there's blanks here. They are not secure against a quantum computer. These numbers are a little outdated, but I just like the setup here. We get to see a little bit of all these different crypto systems that are affected by an adversary with a quantum computer. We have SIDH here as well. That one uses a that is super singularized isogeny, not lattice problems. Throughout the later portion of the talk, I'm going to focus on two schemes in particular that are lattice-based schemes. That's my field I studied, and so I figured that would be probably a good one to work with. So we will actually be testing out some of the security of New Hope and Frodo. I'll show you how we actually arrive at the security parameters for quantum adversaries. Okay. A lot of the time we don't just look at the computational time it'll take for an adversary. We also look at the resources they might need. And it's no different when we're looking at an adversary that has access to a quantum computer. So it's very useful to get down at a level where we're actually considering the logic gates used as well as the qubits used in solving or cracking one of these encryption schemes. I'll start with just a description of a qubit. So we're all used to seeing classical bits. It's either going to be a 0 or a 1. A qubit is allowed to be somewhere in the middle between two. We say that it is in superposition between the on and off stage, so in between 0 and 1. Because we're mostly mathematicians here, and computer scientists, I'm not going to get into the physics. I don't think there's anyone from dynamical systems, so that's okay. I'll use just a linear algebra point of view when discussing quantum mechanics. So a qubit can then be modeled by a two-dimensional Hilbert space. We have the basis vectors. I'm just going to call them, this is Brockett notation or Dirac notation. I'm just going to associate them with two-dimensional vectors. So the 0 state is going to be 1, 0. And the 1 state is just going to be 0, 1. You don't have to use these as your bases as long as you have two basis elements that are orthogonal and normalized. You can use them as your basis for your Hilbert space. Okay. So to represent a qubit in superposition, I'm just representing it as a linear combination of just the two basis states, 0 and 1. Here, the alpha and beta, the coefficients are from complex numbers, but for this talk it suffices just to think of them as real numbers. So these two will be, in our cases, we're not going to be considering imaginary numbers. Okay, and And as you might have heard, we're not able to actually watch this qubit pass through all these gates, and we don't know the result until we actually measure the qubit. And to do that, there's all this physics we need to worry about, but in this case, we're just going to worry about the coefficients to determine the probability if it's going to be measured as a 0 or a 1. So given a particular qubit, and we're going to measure this psi state, there is a probability of that alpha squared that it will be measured as a 0 bit, and a probability of beta squared that will be measured as the 1 bit. So naturally, probabilities all need to add up to 1, so that's why we actually require these bits in superposition to be normalized. So that psi, that's going to be represented as alpha beta, must be normalized to 1. So a quick example of a qubit in superposition. This is the plus state. It's one that appears quite often. You can use this as a basis vector along with the minus state when it's just, instead of a plus here, it's just a minus. So in this particular instance, our alpha and beta are both 1 over square root of 2. So in this particular instance, we have probability 1/2 to measure this quantum state as a 0 and half to measure it as a 1. And I particularly wanted to point out this little purple gate here. This is what is known as a Hadamard gate. We will discuss gates in the next slide. But it's a tool that we have at our disposal. If we have a quantum computer, we can set a bit or a qubit into superposition, which is exactly what I'm doing here to obtain this plus bit. This 1, 0, remember that was our 0 bit. I'm applying a logic gate, as I call it, a Hadamard gate, to put this into superposition. So gates are really our way of manipulating quantum information, as said here. In this talk, we'll be mainly concerned with with logic gates acting on a single qubit. So we're just going to keep our two-dimensional representations of our qubits, and our gates are going to be 2x2 matrices. And we do require that our gates be reversible. This is different from classical computing. We'll get to an example in a bit. But for now, let's consider some quantum gates. Okay, like I said, these all act on one single qubit, so they're just going to be 2x2 matrices. We got a little taste of the Hadamard gate, this is called. This is how we put a bit into superposition when it starts at the 0 state. This is a Pauli Z and X matrices, gates. You might recognize this as it's equivalent to the classical NOT gate. It will turn the bit 0 into a bit 1, and bit 1 into a bit 0. The Z here, it doesn't do anything to the bit, the state 0, but it will turn state 1 into a negative 1. These are probably the prime examples of logic gates acting on a single qubit. We do have requirements. We can't just say that any 2x2 matrix is going to be a valid quantum gate. We require that the 2x2 matrix or any quantum gate is actually unitary. This just means that it's when I take the conjugate transpose and multiply it or apply it to the original gate U, I get the identity back. Conjugate transpose, just have a little example here. That's where the dagger notation comes in. This just means the conjugate transpose of U. So I take the transpose of all my elements in my matrix, which in this case is just negative I and 1, and then I transpose it. Easy enough. And U is going to be unitary if the product of U dagger and U is I. Okay, so if you go back to our logic gates here, it's not very difficult to find the conjugate transpose because we're only dealing with real numbers. But you can work it out yourself. It's pretty straightforward to show that these are all indeed unitary, and so they all are valid quantum gates. And this is actually the only restriction we have on our quantum gate. If it is unitary, it is a valid quantum gate. This brings us to Toffoli gate. Hopefully I'm not butchering that pronunciation. Toffoli. Really, it's good. Really, what we're doing, we're given as input states A, B, and C. And we're looking at a conditional NOT gate here. So a conditional NOT gate, we're really just focusing on, well, are these 2 bits on, or are they 1? If so, we're going to apply this NOT gate. We'll go through a couple examples, but what's lovely about this Toffoli gate is that it is reversible, so we can use it as a possible quantum gate. There is one in particular that we want to focus at. This is a classical NAND gate. I know it looks kind of funky with this slide. This is a classical operation that's not reversible. So what it's doing at this, I should probably explain this product here more. This is just the AND operation. And it works well for this because we're using binary, so if you can think of it as multiplication, that's fine. So A and NAND B is going to consider, well, are they both on? Are they both 1? If so, we're going to negate it. If this is 0 in the middle, we're going to turn it 1. So I made a couple parameters for A and B. There's 2 different cases. A can equal 0, B can equal 1. Well, that will give us A NAND B is equal to 1. Same thing for when A is equal to 0 and B is equal to 0. The NAND will give us 1 once again. So we can't reverse it because, well, 1 will give us 2 different, actually 3 in this case. We can do 1, 0, 3 different cases where the output will be 1. So this is not going to be reversible. But we can use a Toffoli gate to construct a reversible NAND gate. It'll just involve a few extra bits. So we just require that our state here is always set at 1, always set to on, and this will give us the NAND operation and just output the original to begin with. So it's kind of a cool little thing. If you have a phone on you, you can do this along with me. It's kind of a fun little tool if you're using quantum gates. We actually use this in the cryptographers summer camp that the professors here put on. So this just allows us to kind of manipulate some gates in a way. As you can see here, I have my Toffoli gate that I just used previously. I'm just going to go back to that slide. And you're allowed to kind of mess around with it to see, like, what's going to happen if I place a Hadamard gate in front of it. Well, remember that Hadamard gate, it will put, I'm going to set this through. It will put our bit into superposition. So there's going to be half a probability of it being 1, half a probability of it being 0. And that's why it really changes our states here when we look at the Toffoli gate. Well, half chance this is 1. If it is, this conditional NOT is going to go through, and we'll end up with a 0 here. If it is off, we won't apply the conditional NOT, and we'll end up with a 1. So these have to be reversible. Can anyone think what the reverse would be? Maybe it's obvious. Of this NAND gates? Okay. Want to be reversible, so I should be able to apply another gate and get back to what I originally started with.
Self?
Yeah, it's just going to be itself, actually. So you can just add these conditionals. Okay. You can see it'll just be the inverse of itself. So kind of a fun little tool, especially if you're just beginning with I guess, quantum computation. It's called Quark. It's very nice. A bunch of high schoolers learning how to do it, so it must be fairly intuitive. They're very bright too, I guess. So, okay. So that finishes what I want to discuss a little bit about the introduction to quantum computation. I want to go back to now the security requirements for NIST. And we're going to analyze a bit of where they come up with some of these parameters, given that we're going to apply a certain attack to one of these encryption schemes. The ones in particular that I'm going to be considering are going to be the New Hope and Frodo. These are two lattice-based schemes. So sorry, engineers, no isogenies today. But you will learn a little bit about lattices. So I'll give you just a brief introduction. I know a lot of people have seen this already. A lattice is just a discrete subspace of R. So if you take any open neighborhood around any points, it'll just be, I shouldn't say any neighborhood, there is a neighborhood where that point is all alone. And it's just going to be linear combinations of a basis of Rn that have coefficients from the integers. It'll be a little more clear when I look at an example. Typically, at least for this lecture, I'll describe them using column notation for lattices. So if you see a lattice of this form, just know that B1, B2, these are columns of the lattice, and these are my lattice bases. So these will generate my lattice. Okay, just kind of a quick example. Let's say I have a lattice of rank 3. I have 3 columns that are my basis vectors. And these are just my 3 ways of representing them. I just use the integer notation here to mean I can replace any integer there and get a lattice point. Okay. If we look at more of a 2-dimensional aerial view of the lattice, this is a lattice generated by 4, 3, and 3, 1. So you can see where all these points come from. I'm just adding and subtracting these 2 vectors together. So if I wanted to arrive at this point, I just take B1 and then subtract B2 from it. If I wanted to arrive at this point, I just take negative B2 and so on. It's just how I generate my lattice. Of course, the lattices in practice will be much larger and much more complicated than 2 and 3 dimensions. But probably the most famous lattice problem is going to be the shortest vector problem. Okay. And it's exactly what it sounds like. So given a lattice, I need to find the smallest, the shortest. And when I say shortest, I just mean the L2 norm. It's just the distance from 0 that lattice point is. So if I was looking at the previous example, where my lattice is generated by these 3 column vectors, the shortest vector is going to be this linear combination of the basis elements. So when we solve the shortest vector problem, we have found the smallest or shortest lattice point. There's 2 different ways we can do this. Well, there's also combinatorial attacks, but the 2 I will discuss, and I'll mainly focus on the first one, which is sieving. These are 2 ways that we can solve the shortest vector problem of lattices, sieving and enumeration. So both of these can actually be sped up by a quantum computer. It's actually where the estimates for security will come from when we're considering the quantum sieve. You'll notice that asymptotically, this sieving algorithm looks better, right? It's only exponential instead of super exponential. However, for values of smaller n. So if we're looking at smaller dimensional lattices, it might be the case a lot where enumeration is faster. It all depends on the constant in front of the n in the big O notation, which one is preferable. Okay. The main algorithm used in lattice attacks is this BKZ algorithm. And what it does is when it's called on the entire lattice, it focuses on smaller dimensional sublattices. So in this case, I saw it presented this way at a talk. That's why I have 7 here. I'm not referring to the block size 7. Here we're actually going to be using block size 5. Okay. So you can see here, right now I have a lattice of dimension 10. Well, what I call a BKZ algorithm on it. This is going to give me shorter, more orthogonal vectors. I focus on the first 5 basis elements in the lattice generated by them. I find the shortest vector, and I put it there. And then I move on to the next block. I call my shortest vector problem solver, find the shortest vector, put it where B2 is. And then so on and so on. And when I finally reach the end, this is called one BKZ tour. Okay. And we can do this multiple times until we get a lattice satisfying the condition we want. Hopefully where the shortest vector is going to be placed at B1. So this is the main algorithm used when considering lattice attacks on these crypto systems. So naturally, we want to look at, well, how expensive is this attack going to be? The entire algorithm is going to be dominated by that small shortest vector problem solver. So when we're focusing on a smaller dimensional lattice instead of the big picture. So we actually want to look at the complexity of a shortest vector problem solver instead of BKZ as a whole. So one of them that I mentioned was a sieving algorithm for solving shortest vector problem. Like I said, they were exponential, but they give us a good lower bound starting point to these security requirements. So we can see that a lower bound for an attack cost is going to be whatever that block size necessary is, so the dimension of the lattice we're looking at in each sublattice routine, times some constant, as the exponent of 2 is going to be our computational cost. So there are a couple different sieving algorithms I need to discuss. First, the classical sieving algorithm. This constant here is going to be a 0.292. So when we're considering classical attacks, we consider when this C here, the constant in the big O notation is 0.292. And then there's 2 quantum cases, and I separate them because in theory, the second one for the 0.265, this is the best known attack against a quantum, or with a quantum computer against SVP. However, this attack requires a storage cost of 2 to the CB, where C is actually this 0.2075. So no matter what, sieving algorithms are going to have to store a certain amount of vectors, and that storage requirement is what is represented here by that worst case quantum. Okay, so so no matter how fast of an algorithm we run for sieving, we're still going to have to worry about storing 2 to the C beta vectors, where this is our C value. So it's still quite a lot to think of. That's why I consider it worst case quantum. Okay. And just the log 2 cost is mostly what we represent, or how we represent our security parameters. So the attack that I consider on the encryption schemes that are based on lattice problems would be called what's known as a primal attack. I won't go into depth for this one because it gets fairly complicated, but the idea is it takes the underlying problem that New Hope and Frodo are based on. So while the underlying problem of psych would be the SIDH, underlying problem of New Hope and Frodo are respectively ring learning with errors and learning with errors. Frodo did something fun with that. They want to get rid of the ring, so they call themselves. Yeah, Lord of the Rings reference. But so really, the two problems are both reduced to a SVP problem for lattices. That's what the primal attack does. It takes that underlying problem and converts it to a lattice problem. There are multiple methods to find what block size needed. What block size is needed to solve the instance using that BKZ algorithm. They'll be in the references, but I did it by myself to just find the betas necessary. So to launch a successful, is that yellow? Show up okay? Good. So to launch a successful attack on New Hope 512, the block size needed in the algorithm is going to be 386, which means we look at a lattice of dimension 386. And Frodo 976, given that the parameters of that encryption scheme, the beta necessary to solve that instance is going to be 707, and that's going to be the size of the lattice that we consider. And again, we have just the classical worst case and quantum cost listed here. There's actually some great resources. I'm really utilizing this QR code thing today. But, oops. It's not letting me copy that. There's a really nice resource when you're looking at the cost of the attacks on the NTRU and LWE schemes, so the lattice schemes. I just want to show you that quick. Here it is. This is done by Martin Albrecht. It's all, it really is useful if you're trying to understand what attacks you're looking for. So if we just want to compare with what we got, we can just find New Hope, for example, and we'll describe our attack type. We were looking at the primal. Okay, so this here represents the quantum cost, not the worst case, and this is the classical. So we should have a classical cost of New Hope for 113, and and 259 for the quantum. Oops. Did I mess it up somehow? 113 for classical and quantum cost of 103. Yeah. Just kind of a useful tool. If you want, you can check out all the lattice-based schemes here. This is why lattice-based cryptography is, I guess, very difficult right now to actually establish good security requirements. These are all the proposed cost ones, so there's quite a lot to deal with. And they're all just given different cost models. If we're looking at vector addition for Frodo, for example, Frodo thinks we should consider something like this, for example, where there's just that extra plus beta in the exponent. Okay, so this is kind of a useful tool you can use, and kept it kind of brief today. Hope that's okay. But here are my references. Happy to answer any questions.
Thanks. Any questions?
I have a question just about this last thing, because the 512 parameters are claiming security level 1, but that's below level 1, right? So what is the matter here? Or am I missing something? New Hope 512 should be category 1.
Oh, so you're,
It should be 128.
the quantum wire, right?
Or even in classical is under 128.
Right, so classical is under 128 exactly.
Oh yeah, I agree.
Yeah. So okay, so they
Yes,
do it
yeah.
for estimate or
So what happened on here? Maybe I got it wrong. Thought I got it.
Yeah, so we,
No, I think that's alright. That's figure 6.
Oh, okay. Well, yeah, for classical it would be 113.
yeah, that's really not good enough. But okay, but maybe this depends. Maybe you can comment on why, because for New Hope it has to be a power of 2, so maybe they're constrained by that.
Well,
That doesn't really give any good.
you want me to explain why New Hope has to be powered?
Yeah, I mean.
Oh, why you can't do
Okay.
something in the middle? Yeah, because well, New Hope is a ring over a cyclotomic field, x to some power of 2 plus 1. It's just I think they get a lot of useful properties from cyclotomic field extensions from there, and just from having your cyclotomic number field over 2 to the n plus 1, right? So yeah, I guess New Hope, in order to establish a secure ring line with their assumption, they always need to be over that ring. So they really don't have many choices. They have 512, 1024, and then 2048. So they can't really
And that's it.
do anything in between, yeah.
Any other questions, comments? Yeah.
Yeah, can you go back to the BKZ algorithm? Yeah, so, maybe I'm not completely understanding it, but to me, it sort of looks like the sorting algorithm. Is that what it is?
No, nothing's, I guess the sorting comes in, we go through a process called size reduction, but really we're just finding that we're not moving any of these vectors around until we replace V1 with the shortest vector. That's really the, I can't really think of any sorting that goes around besides that. But yeah, we're really just looking through this lattice, finding a short vector, and then that's what we replace V1 by, if that makes sense. And then we move on to the next.
just on a different slide than that last slide that you were at, when you mentioned the worst case, those numbers are always smaller. I guess I'm confused what you're referring to as a worst
Yeah,
case.
so when I look
Yeah.
at quantum cost, I look for a lower bound of just like the time complexity of it would be 0.265 times the dimension of your lattice.
Okay.
And the worst case would be 2075 times n. This one is going to be the resource requirement you need. So both of these are sieving algorithms. This is going to be the time complexity used to solve one of these instances. This is going to be the number of vectors that you need to store to actually successfully launch a sieve attack. So we assume that, well, maybe this might get better, you know. Like, well, how good can this actually get? Let's just assume it gets as good as it can possibly be.
Okay.
Let's pick up this one instead, because we know no matter what, they're going to have to store this information. And that's exponential, so we can't allow that. Does that make sense?
Not really, but.
Well, sorry, there's a difference between like the resources you need and also the I guess, time it's going to take to run through the sieving algorithm.
So those two things represent two things for, because I guess I'm just confused because
Yeah, you
you're
can-
saying there's two different algorithms. You were referencing one as the time and one as the memory.
I guess the algorithmic complexity, would that be better? Like I'm looking at the algorithms used in this one,
Okay.
not the storage requirements. this is the storage requirement for the CU.
Okay.
So no matter what, I can run this, and I know like maybe this is going to be fast enough, but I can make this as fast as I want. If I adopt this one as my worst case, I know no matter what, no matter how fast that calculation gets, I'm still going to have to store these.
I'll
Sorry,
have to think about it more, I guess. It still doesn't make sense to me, but that's fine. It's just me.
Sorry, I don't know if I
No, yeah, it's fine.
explained it correctly.
Is there any more questions? Yeah.
I mean, for an explanation for this, the difference of these two numbers, 0.265 comes from, obtained by a random walk algorithm using the quantum computers. Am I right? Do you know the?
No, I think the 0.2075 algorithm memory requirement comes from some
No.
geometric.
The time complex is 0.265 times something. Is it because of the using a random walk algorithm?
I think from what Shaun described, this is a memory-heavy algorithm, so that's not a random walk.
No, but he's asking like where this complexity comes from. Where the 0.265, where does that come
From the seeding algorithm. By
Seeding
combining the vectors, I guess, right? So we have lots of vectors, and we combine them like more combinatorial way, but together with some geometric information every time we try to reduce it. So I think what Shaun said is correct. So for the memory requirement, there are some arguments saying that without such many vectors, there's no way to find the shortest vector. That's why this memory requirement seems to be the minimum one if we stick to this algorithm.
Okay, I got this point.
Thanks.
More questions? Comments? Do you know if this intro paper estimate in intro paper has an estimate for the quantum enumeration algorithm?
I only saw the seeding.
So they only put the quantum saving over there.
Right. And they actually don't consider the worst case scenario
Okay.
also on their website. I don't
Okay.
know if that's necessary or not, but
So these complexities are for random lattices or?
yeah, they would be for random lattices, yeah.
You always assume that your
Are they?
cryptographic instance looks random.
Are they for random lattices or any assumptions about the lattices?
There is no assumptions about the lattice. Just random ones. It should work for any, I think. Well, we make assumptions on the lattice structure for these attacks, but not for the complexity arguments.
Is there anything known for cases where you can make assumptions about lattices and improve the complexity? Reduce the complexity.
Yeah, I guess if, like, for example, we're given an instance of LWE, we know that the lattice isn't going to have a shortest vector that's typical. If we reduce it from LWE to USVP, it's actually going to be a lot smaller. So that changes our ability to actually find that smallest vector. We might not have to use, I guess, as strong as an algorithm to find it. But so in that case, I think we really need to be careful on what kind of lattice we're working with, just when we're establishing the data, because then we can make assumptions about our lattice. But I think in the complexity arguments, they just take any n-dimensional lattice.
So this is the equivalent of, say, ISD, where you put just like a generic attack on a random instance, essentially.
Yeah, I think the pretty much assumes that. Yeah.
Okay.
Any more questions?
So I have a question about NTRU. So NTRU in the first versions of NTRU had some symmetry, right? I mean, there was a symmetry in the base, right? That would reduce the complexity. What's the current situation with Entru? I mean, what's the latest?
Yeah. I'm not sure.
Yeah. I guess we, do we have, Shaun, do you know if we have the Entru estimate on the, of course, they should be appear on the paper, right, by Martin.
Right.
Maybe we can just go over the security of this Entru.
You wanted this website?
Yeah, just I think that maybe. I don't think there's an attack. Using the symmetry, we can improve a factor of order n, where n is dimensional like this. That's the best we can do. There's a polynomial improvement. There's no exponential improvement using the structure. Actually, that's a good question because I think that's one topic people try to understand how to use the structure.
There's also an option that ends in the beginning, in the first row, not about this.
Yeah.
Oh, yeah.
Yeah.
So maybe that refers to Entru HRSS.
Yeah, I'm not sure. I only briefly looked at it for the New Hope parameters, but
Okay.
I'm not sure.
Yeah, okay, that seems still strong enough.
Yeah, I guess I'm not up to date on Entru. Perhaps I should be.
Okay, any more questions? So, no more questions. Let's thank Shaun again.
So yes, thanks Shaun, and we can stay and discuss a couple of things. I think to clarify, I will stop this.